And hi, welcome OpenFoamers. Welcome to this video discussion on the chtMultiRegionFoam. So we are doing the hot sphere in oil case, and we're trying to validate it against empirical correlation. And it was found in the last video that the source of the bug I've been trying to find for the last tens of videos is actually a round-off error in the thermophysical properties. So that was explained in the last video. So this is the results, more of the results of comparing this new heat transfer coefficient results against temperature and trying to get the Nusselt number, Rayleigh number out. And of course, yeah, we want to compare that against the empirical correlation. And do keep in mind, this is just using a laminar model. There is no turbulence model being put in it yet, despite the Rayleigh number being pretty much in the turbulence zone for the first at least 30 seconds. Because at least from this simulation, we have the temperature about 400 Kelvin at 28 seconds. So it looks like the heat transfer coefficient has jumped several fold and continues to be at least over 100 throughout this simulation. Now this is a good sign because that's definitely closer to our empirical correlations than what we had before. And what we had before was a very underestimated Nusselt number as compared to the Rayleigh number. But of course, this time, maybe instead of comparing to the Rayleigh number, I'll compare it with temperature. It will be maybe a more consistent way of doing things. But let me just show you. Okay, let me just show you the results. But while I do that, I'll just do a git add and commit. All right. So let's see. This is our sphere. And this is where we are. We can reset to normal. Okay, it's lagging. It is lagging. Okay, there you go. All right, this is our sphere at the end of the 300 seconds. It's pretty much cooled to around 307 Kelvin, which is pretty much not so interesting to us anymore. And lagging again. Hold on. Yes, let's see. This is our temperature at T equals to 2. You can see that the sphere is pretty hot, and already you see the boundary layer forming and there is convection happening, which means, yeah, the fluid is a lot less viscous than before. It is a good result because the boundary layer is pretty thin and there is some flow there, which is very good. Okay, so I'm going to try playing. Hopefully it doesn't lag out on me. Okay, so this should be at 4 seconds, and you see the little thing actually rise up a lot. So within 4 seconds, you see the plume actually rise to the top already. So this is a temperature dependent thing. And the fine mesh does show the resolution a lot nicer. So you can see it's pretty much that same picture. I'm sorry for the lag, but it's pretty much the same picture throughout all, let's say, 300 seconds. Okay, so it's a pretty good result. You can see the sphere cooling off pretty quickly, and the fluid is just leaving the sphere's surface, going all the way to the top. Now I think that's enough of it. The rest of the way through, it is pretty much the same picture. You just see the sphere getting cooler and cooler, and the convection currents continuing to move. If you are interested, I mean, you can see the U partial, which is the velocity, and it will take another while to load. And this is what it looks like. The velocity is on the order of magnitude of about 0.1 meters a second. That means a 10 centimeter a second kind of a movement from the sphere to the top. So And you can see it with the mesh. Very good. This is the fine mesh version. So you can see with the mesh, it's very well resolved, these boundary layers, etc, etc. So we don't. So the problem wasn't actually the mesh. This is actually a pretty decent mesh as far as meshing is concerned. When you want to resolve the boundary layers and of course the stuff on top. Yeah. So what we want instead now is to compare the results. Okay, so let me open. Okay, I'll close this window. Okay, and I'll go to my file. Okay, and we will want to open the GitHub folder. So that's where we are, GitHub folder, OpenFoam Heat Transfer, CHT, and I'll look at the snappy case. Is that? Okay, it's not in the snappy case, it's in the experimental case, if I'm not wrong. So the experimental case is where the test was successfully run. So yeah, successfully run. So let's look at the experimental case. Now I'll probably rename this to a laminar fine mesh case, because this looks pretty successful. So let's go to post-processing. That's where we find our all-important Nusselt number. Okay, surface field value. So this is the Nusselt number versus the average surface temperature, which I think by now you know that the Biot number is less than 1. We can of course test that again, but yeah, as you see from the cross-section temperature variation of the sphere, it was pretty much a uniform temperature, so we can guess the Biot number is definitely less than 0.1. Sorry, less than 0.1. So you can use a lump capacitance method for copper sphere in this Dalton oil. I'm going to copy all of this data. So there we go. And I'm going to put them here in this file or folder. Okay, so these are the two ways of calculating the heat transfer coefficient. Now a few things to do. I'm going to rename this graph just for orderliness sake. Temperature and heat transfer coefficient versus time for round off error in thermal, physical properties, and coarse mesh. Okay, so I want to keep all this data because that will show you the sensitivity of this problem to the coarse mesh and everything else. So let's see. We'll put. Yeah, I copied the time data, so I'll just put it here. Okay, so this is coarse mesh and wrong. Okay, coarse mesh. Thermal physical data, round off error. And then I can just delete all of this because this is, oh well, yeah, delete this because it's no longer relevant. That was just to show, you know, the two ways of calculating the heat flux. One from the wall method, wall heat flux method, one from this average heat transfer coefficient method. and we saw that both were pretty much congruent. So that part is done. Okay, so I will put that there, and this I will just say it's a wrong method, but it shows that the wall heat flux method is the same as the wall heat flux method is the same as the average heat transfer coefficient method. So wall heat flux method. So this one is important. It's still valuable because it compares two methods of calculating the H value, heat transfer coefficient value. Okay, so there we go. So yeah, we saw that before. So now we have a fine mesh and a coarse mesh. Okay, so we have a fine mesh, corrected thermal physical property, and git commit. Okay. Now, for future reference, of course, we should know that this is a laminar flow, no turbulence model. Okay, no turbulence model, so we can see clearly the effect of adding a turbulence model later on, because technically speaking, it should be turbulent. So I'll just do heat transfer coefficient, and I will just make it not negative, minus this, and I'll go all the way down. Alright, then we'll look for one more, which is the I want to open Notepad for the coarse mesh one. Okay, this one's the wrong way. I don't want to navigate again. Okay, I'll put the coarse mesh sphere oil. It's also been running for 300 seconds. Let's go to surface view value. And you see the heat transfer coefficient is a lot lower. So I'll just do this coarse mesh. Okay, let me double check whether those properties are correct. Coarse mesh sphere oil. Just double check here. Constant oil thermal physical properties. Wait a while. Alright, so I use the 10 decimal place method, which is pretty gets rid of all the gets rid of all the errors when it comes to rounding off. So this is a good good one. Alright, so I'm gonna put this here. Coarse mesh corrected thermal physical properties. Now of course we do a laminar one as well, and H, I'll just do a H here, and this is weird. It seems to be printing my average heat transfer coefficient in the second what do you call that, second part, but no matter. Yeah, doesn't matter. So as long as I have the temperature and the heat transfer coefficient, it should be fine. Okay, minus this. So that's about 77. 78 is pretty low. And let's superimpose this on the graph. Okay. I mean, yeah, let's see. Coarse mesh. All right. I'll copy and paste this graph, and then I'll want to add coarse mesh here. So that every of those will change. Okay. I'm just going to do a graph comparison. You can see trends very clearly. And then go to select data. Add one piece of data, series name, wrong thermophysical data, round off method. This is the one. Series name is this. Okay, average temperature. X value, I will use time. Y value, I'll use the temperature. And this one, I will use heat transfer coefficient here. X value, I will use time. Y value, I'll use the heat flux transfer coefficient. Yeah. All right. And just take a look at that. And fine mesh. So I'll just say this is a fine mesh. Fine mesh. Now plot that on the other graph. Format data series. I'm going to plot it on the graph to the right. Plot it on secondary axis, primary axis. Oh yeah, it is plotted on the secondary axis. Okay, good. Then this should be also plotted on this primary axis. So, okay. It's getting very messy, but let's give it a different marker options. I'll give this maybe the square shape, built-in square. Oh man. Okay, so just a bit of data analysis. You can see that the heat transfer coefficient is severely increased because of the corrections you made. Of course, it tapers off over here where the temperature is pretty low. Okay, so that's what the fine mesh one is like. And of course, let's do the coarse mesh as well. Design. I'll zoom in a little bit. Okay, and now we'll, oh man, design, select data. Series name average. Oh, this is not the find map. This is not the one I want. This was the one I want. Series X values is the time. And series Y values will be temperature. C6, no, it should be here. Okay, and one more. Did I just cancel my old? No, good. Add. There we go. One more is this. Time for X values and this for Y values. Okay. Okay, there we go. And of course I'll need to do some renaming. And I'll just say this is a cost mesh. Mesh course mesh. Okay, there we go. Should not be an issue now. And there we go. This should all be where is this? H cost mesh should be on the secondary axis. This should be T is on the primary axis. Okay, so let's do comparison. And the temperature first. Okay. I will color the lines maybe orange. Okay, just that you may see. Solid line color orange. Different shades of orange. Another shade of orange. And this one I'll just say it's red. Okay. So this one is the coarse mesh plus coarse mesh and wrong, round off error. So you can see it has a very big impact. This is one with the coarse mesh with the corrected thermophysical properties, but yeah, you see the boundary layer is not well resolved, so it doesn't cool off as fast as the fine mesh one. Fine mesh one is likely the most correct, and it cools off the fastest, and it has the highest heat transfer coefficient. This is the H for the coarse mesh, which we can color it a different shade of blue, and this is also we can color. This is also one of the heat transfer coefficient. It's the coarse mesh, but it's wrong thermophysical properties. So see, it's very important that we do the rounding off error. We watch out for those in case you have a situation like this happen. And now we want to convert all these into Nusselt numbers. So yeah. Okay, so this will be based on the surface temperature. Okay. Okay, so this one assumes that the Nusselt number and Prandtl number, Grashof number are calculated based on the infinite fluid temperature. but normally we want to use a film temperature, so we'll use this spreadsheet instead. Okay, so this one is again with the coarse mesh, and it doesn't quite match up here to the correlation. All right, so you can put this as coarse mesh data. Okay, so this one doesn't matter anymore. It's a bulk temperature. I can just black this out because it's not relevant. So okay, I want to add series to this. CFD laminar coarse mesh round off error. So I just note these correctly. And then next thing, we'll need to input surface temperature and heat transfer coefficient data, which is exactly what we have. So let's go surface temperature. This is a coarse mesh and heat transfer data. Okay, so I'm just going to say this one's the corrected thermophysical properties coarse mesh, and I'll do the heat, H as so. I'll paste the values in. Now I'll use these headers on top. Okay, so now I need to do a T-film plus T-bulk average. So I just copy and paste the formula over. Okay, then I'll have a conductivity of the T-film, which is here. I'll paste it in. Nusselt number of the T-film. Paste it in. Dynamic viscosity is this very long one. I'll paste it in. Now, good thing spent all that effort writing these properties correctly, so that yeah, come time like this, you can just copy and paste it in. Okay. Right. And this is the rho dt, then we can get beta, and we can have the Grashof number really quickly. So you want to see how this spreadsheet is done, please see the videos few that I did a few videos ago. So this is the Rayleigh number. So we got a correlation and CFD laminar. This one is just coarse mesh. Okay. Alright, I mean, we can do a graph first that compares Rayleigh number versus the Nusselt number for whatever Prandtl number is given. That we can just add select data, add an entry. So the entry will be named coarse mesh corrected thermophysical properties. Or I can use this instead. CFD laminar. I'll have the Rayleigh number here, add it. It's the X value. We can compare against temperature later, but for now, Rayleigh number will suffice. And cancel. I'll put OK. So we see the effect of round off error. Okay. So the effect of let me enlarge that graph. Alright, okay, so you can see that if we correct this round-off error, across the board, the nozzle number increases as compared to the Rayleigh number, okay? But it's not quite as close as what we desire to be at the correlation over here. So it does give us some improvement, yes, but we'll need the fine mesh data as well. And I'll talk about that in the next video because it's already 30 minutes, so I want to continue discussion later on. Thanks for watching. I'll see you guys again shortly. I mean again, yeah. Okay, bye-bye.